Welcome to lecture number 12 for ECE 341 Random Processes, LaPlace Transforms. So going back to the syllabus for random processes, what we've covered so far is combinatorics, discrete probability events like rolling dice, flipping coins. We're now going to switch gears. We're now going to look at continuous probability functions. So some things are digital, discrete, like rolling a die. I get a 1, 2, or 3. Some things are analog, like if I measure temperature or pressure, flow, light. Those are all analog signals. If I take a resistor, if it's a 1K resistor with a tolerance of 5%, it could be 1K plus or minus 5%. The values you can take on are continuous. So when you have continuous functions, I need mathematics that can describe continuous systems, continuous probabilities. That's LaPlace transforms. Again, for discrete probabilities, we would use the z-transform. For continuous probabilities, we use LaPlace transforms. Now in statistics, these are called moment-generating functions. In electrical computer engineering, we call them LaPlace transforms. I'm going to stick with the word LaPlace transforms. And LaPlace transforms are used throughout the curriculum. For example, if you look at the courses you need to graduate in computer engineering, you start getting LaPlace transforms in Math 166, and then use them in 265, 266. We use them in this class, random processes, used in, I think circuits 2 is when you start using LaPlace transforms, used extensively in signals and systems, and a couple other courses. So electronics uses them for filter design. Quite a few courses use LaPlace transforms. Now in these courses, the LaPlace transform is used to analyze differential equations. In random processes, it's used to analyze continuous probability functions. But it's the same thing as LaPlace transforms. So I'm going to be using the term LaPlace transform. In statistics, they would use the term moment-generating function. Same thing, I'll just stick with the word LaPlace. So hopefully it doesn't cause too much confusion. So starting out, the LaPlace transform assumes that all functions are in the form of e to the st, and that's for time greater than 0. This results in derivatives of y being s, e to the st. Where that's significant is LaPlace transforms turn differential equations into algebraic equations in S, and the assumption is that algebra is easier than calculus. For example, suppose I have the following differential equation. X and y are related to each other, but the relationship is differential equation. And this is actually really common. Almost the entire world is described by differential equations. Think about it, if I have a static system, that would be something like y is 3 times x. That's a static system. If x jumps, then y jumps as well. Now, most systems don't do that. They have inertia of one form or another. So if you have a step on the input, it takes the output a little bit of time to respond. If that's what you have, that's a system described by a differential equation, which is pretty much everything. So, in my opinion, calculus is fundamental. Everybody should have calculus. In fact, in Russia, calculus is required to graduate from high school. It's that fundamental. Now, as you're noticing when you take Calc 1, Calc 2, Calc 3, calculus is not easy. It's important because calculus describes the world, but not easy. What LaPlace transforms do is they turn calculus into algebra. So suppose I have this differential equation. If I substitute s for a derivative, then the third derivative becomes s cubed y, second derivative s squared, first derivative y, derivative of x, and x. And this assumes 0 initial conditions. Once I have a function in s, I can use algebra. Factor out the y's, factor out the x's, solve for y in terms of x. So this is the relationship between x and y using LaPlace notation. Now I can treat this as a gain. Essentially, x is amplified by some gain to get to y. So this part right here is up until called the gain, g of s. It's a function of s, which means it's a function of frequency. It's a filter. And note that this goes both ways. If I have a differential equation, I can give you a transfer function. If I have a transfer function, I can give you a differential equation. So if here's the transfer function between x and y, that means a differential equation. Cross multiply, note that s means derivative, so there's the third derivative of y, second derivative, first derivative, just y, derivative of x, x. So that differential equation is the same as that transfer function. It's just another way of writing the relationship between x and y. So anytime you see a transfer function in S, think differential equation. Now kind of a sidelight, S means derivative. So when I have S, that means the first derivative, second derivative, third derivative. You have to have powers of S, or integer powers of S. So like S squared means the second derivative of y. I can't have fractional powers. S to the 2.3 means the 2.3th derivative. I know what the first derivative is. I know what the second derivative is. I don't know what a 0.3 derivative is. Now actually there is a branch of mathematics that claims you can take partial derivatives, or fractional derivatives. The argument is the first derivative is a 90 degrees phase shift, so a 0.3 phase, or derivative is a 27 degree phase shift. I don't buy it, but some of you might know an area of mathematics that claims you can do it. As far as I'm concerned, as far as this curriculum in electrical and computer engineering is concerned, you can't do it. So you're stuck with integers when you have powers on S, at least in this major. So as an example, this is where transfer functions Laplace notation is really useful. Suppose I have x and y are related by a differential equation defined by this transfer function. Suppose x is a sine wave. Solve for y. Now there's a couple ways of doing this. What you would do back in calculus is if I have a differential equation in this form, I know x, I will guess the answer for y. I'll then take the first derivative, second derivative, third derivative, substitute, match the coefficients, and if I guessed right, it'll balance. If I guessed wrong, I got to guess something else. That's one way to solve, kind of the painful way to do it. There's an easier way to solve this problem. This is using a thing called phasors. Now, if the input was a complex exponential, that'd be nice, because the derivative of e to the st is just s e to the st, second derivative is s squared. I like exponentials, but that's not an exponential. From Euler's identity, e to the j4t has a real part and a complex part. If I just take the real part, then e to the j4t means cosine. So in phasors, 1 means cosine. If I multiply e to the j4t times a complex number, a plus jb, and take the real part, what I get is a times cosine, here's the j squared, minus b times sine, plus the cross terms j times something. If I just take the real part, then a plus jb represents a cosine minus b sine. So in phasors, I can represent sines and cosines with complex numbers, and that assumes my input is e to the j4t. And when I do that, the real part is cosine minus j is sine. So this is a hard problem to solve. I'm going to change the problem. Let's pretend the input is a complex exponential. Take the real part to find x, take the real part to find y. So what I have is, for this problem, this is true for all s. All I care about is what's the gain when s equals j4. Again, remember that x of t is 3 cosine of 4t. So that'd be the frequency right here, 4, is s. Assuming everything's e to the st, this must be s is j4. In terms of x, in phasor form, the real part's cosine minus j is sine, so x has 3 cosine, 0 sine, there's x. This is the relationship between x and y. All I care about is what's the gain at 4 radians per second. Times the input at 4 radians per second. Analyze that, I get a complex number. What that complex number means is real parts cosine minus j is sine. So that's exactly the same answer you'd get using the techniques in calculus. But in calculus, what I'd have to do is guess that y of t okay, what's going on here? My keyboard's not working. We're going to try it again. Guess y of t is a cosine of 4t plus b sine of 4t. If I make that guess, I can take the derivative, second derivative, third derivative, substitute, solve for a and b, and it balances. Any other guess, it won't work. That's one of the problems with calculus. You have to guess the right answer to find the right answer. It does work, but it's tedious. This is a way to find the answer that's much, much easier. That's phasors. That is introduced in Circuits 2. No, I should say, introduced in Circuits 2, used in electronics, embedded systems, signals. Pretty much from that point onward, we'll be using phasors to analyze circuits and differential equations. Now note, this is a function of s. If s changes, the gain changes, the output changes. So let's repeat. Suppose instead I said x is 5 cosine 20t plus 6 sine 20t. Using the phasor approach, what I would do is, here's the gain everywhere. All I care about is what's the gain at 20 radians per second. So analyze at s equals j20 times the input. The input in phasor form, the real part's cosine minus j is sine. So this is represented as 5 minus j6. Analyze it, I get a complex number. Real part's cosine minus j is sine. Pretty easy to solve. And note that this is a filter. A filter just means a circuit where the gain changes with the frequency. I change S, I change the gain. Some frequencies are amplified, some are attenuated. You use that in Circuits 2 and electronics to design different types of filters. I can build a low-pass filter, high-pass filter, band-pass filters, like for your subwoofer. The subwoofer has a filter that passes low frequencies to the woofer, everything else to the mid-range and tweeter. Anything described by a differential equation is a filter. Now, differential equations are linear. What linear means is that if I have f of a plus b, that's f of a plus f of b. That's what linear means. Suppose I have this problem. My input contains two different sine waves at two distinct frequencies. Find y of t. Well, what I would do is use linearity and superposition. Treat this as two separate problems. Here's the first problem. If that's x of t, find y of t. Second problem. If this is x of t, find y of t. Take the two answers, add them together. That's the total answer. So I don't really have to analyze this. I've already done that. Here's the first answer. Here's the second answer. There's y of t. And one thing to note, a mistake that people oftentimes make is they'll take the first answer, 0.544 plus j.946, take that number right there. That's a complex number. Take the second one, that's a complex number. The total is the first answer plus the second answer. Add those two complex numbers together and get a complex number. You would think that would work. It doesn't. The reason that doesn't work is the first complex number represents the sine wave at 4 radians per second. The second complex number represents the sine wave at 20 radians per second. When you add the two together, it doesn't simplify. I can't combine these terms. That's basically saying that all sine waves are orthogonal. They don't combine. So that's kind of one example of where you use LaPlace transforms. That's what you do in circuits, signals and systems, many other courses. And what LaPlace transforms do is they turn calculus into algebraic equations in S. And again, the assumption is that algebra is easier than calculus. LaPlace transforms will also be used in this class, random processes. Now, like the Z transform, if I want to find, well, in random processes, we call this the moment generating function. If I want to find the moment generating function for PDF, I take the Laplace transform. If I have the Laplace transform, I want to find the PDF, I take the inverse Laplace transform. In the Z-plane, we had a table of Z transforms that we used with Laplace transforms. There's also a table that we use. So here's the table of Laplace transforms. Delta function is just 1. A step is 1 over s. A ramp, t, is 1 over s squared. T squared is 2 over s cubed. E to the minus bt is 1 over s plus b. T e to the minus bt, 1 over s plus b squared. T squared e to the minus bt is 2 over s plus b cubed. And there's more of them. Go to the handbook, CRC Handbook of Chemistry and Mathematics. They've got 20 pages of Laplace transforms. This is going to be enough for this class. In addition, I could have complex poles. If a pole is complex, in this class it'll always have the complex conjugate as well. Doing this one, doing some algebra, you can eventually find that the inverse Laplace transform of this is the real part of the pole is your exponential. The complex part of the pole is the frequency. The amplitude times 2 is the amplitude. And the angle, it's actually the angle over the minus jc, is the phase shift. So with this table of Laplace transforms, I can solve most problems. And kind of a sidelight. I mentioned that most complex poles have a complex conjugate. That's a property of polynomials. If you have real coefficients for polynomial and you find the roots, if one root is complex, it will always have the complex conjugate, and you need that so the complex terms disappear. Now that's what you're going to find in pretty much every class except for communication systems. And the reason you get a complex number without its complex conjugate in communication systems is this. If I take an audio signal, that's like your 20 to 20 kilohertz bandwidth. So this is frequency, there's your audio component, plus it'll have its complex conjugate. That's what audio looks like in the frequency domain. Now to do AM radio broadcasting, what I'll do is I'll modulate this at a megahertz. So the carrier frequency is, say, 1 megahertz. And I'll have the upper sideband and lower sideband, the complex conjugate, centered at 1 megahertz. Well, when I have a radio station, if I transmit this, this is going to take power. This takes power, that takes power. If I could eliminate the lower sideband, I wouldn't lose any information. But I would cut the power demand by half for the radio station. It makes the math really ugly, because I now have a complex number without its complex conjugate. But if I can figure out the mathematics, I can cut the power consumption for radio stations by half. So that's kind of one place that you see complex numbers without their complex conjugate, communication systems. That's upper sideband transmission. That's a different class. Almost every other class, you'll always have complex conjugates for any complex number, including this one. So let's do a couple examples. Suppose I have x and y related by a differential equation. So y is 5 over s plus 3 times x. Find the impulse response of this system. Well, the approach is I go back to my table. If x is an impulse, the Laplace transform is 1. So I replace x with this Laplace transform, and there's the Laplace transform of y. Once I know the Laplace transform of y, find the inverse Laplace transform. So go back to my table, and here's the entry. So the answer is going to be 5 e to the minus 3t for time positive. And that's what the impulse response looks like. Another problem, find the step response. Now, in terms of statistics, this would be a PDF. Find the PDF for y, assuming an initial condition. And that's what the PDF would be. If I want to find the step response, I take x, replace it with a Laplace transform of a step. That's 1 over s. And that's Laplace transform for y. In probability, this is integration. S means derivative. 1 over s is the antiderivative, or integration. This would be the CDF. This is not in my table, so what I do is I use partial fraction expansion. I know the answer is going to look something like a over s plus b over s plus 3. To find a and b, I use the cover-up method. Cover up the s, plug in s equals 0, I get 5/3. To find b, I cover up this term, plug in s equals minus 3, I get minus 5/3. Now these are in my table. The inverse Laplace transform is 5/3 minus 5/3 e to the minus 3t for time positive. Now in statistics, you can get repeated roots. There's a couple ways to get repeated roots. If you have a differential equation, the differential equation is a function of the capacitors, inductors, resistors for a circuit. And it is possible that the differential equation will have repeated roots. It's highly unlikely. Repeated roots just means you picked R, L, C such that the roots are exactly equal. And the probability of that is basically 0. You can get repeated roots in statistics as well. For example, if I have 1 over s plus a, that corresponds to an exponential distribution, such as the time it takes for an atom to decay. If I want to find the time it takes until 2 atoms decay, that'd be 1 over s plus a squared. 3 atoms decay cubed, 4 atoms to decay to the 4th. So in statistics, you can get repeated roots. If you have repeated roots, the inverse Laplace transform is t to the n e to the minus at. Now when you have repeated roots, I can find the highest power using the cover-up method. The other terms, you have to use some other method, such as placing over common denominator and matching terms. So let's do an example. Suppose I have this system. Find the inverse Laplace transform. Well, I know what the answer is going to look like. I've got a pole at 1 over s, 2 poles at minus 2, s plus 2 squared. There's going to be a third solution. I could have just 1 over s plus 2. The right-hand side is equal to the left-hand side. A and b are easy to find. Just use the cover-up method. As s goes to 0, a must be 4 over s plus 2 squared. A is 1. To find b, as s goes to minus 2, that'll be this guy right here. That's 4 over s. As s goes to minus 2, b is minus 2. C is a little bit harder. There's a couple ways to find c. The method I like is place over a common denominator and match coefficients. So I found a and b. A is 1, b is minus 2. C I need to find. So the left-hand side and the right-hand side have to match. So what I'll do is place this over a common denominator, multiply 1 over s times s plus 2 squared, middle term times s over s, last term times s plus 2. Denominators are all the same, so I can add the numerators. The numerators have to match up, so 4 must be equal to s plus 2 squared times 1, plus s times minus 2, plus c times s plus 2. Solve for c. And there's actually 3 terms, the s squared, s, and constant term. All 3 of them have to match. Let's take the easy one, the s squared term. This is 0s squared is equal to 1s squared, nothing, plus cs squared. So c must be minus 1. So here's c, here's your partial fraction expansion. And now I can take the inverse Laplace transform. This is 1 over s minus 2 over s plus 2 squared. minus 1 over s plus 2. There's y of t. Let's do another one. If I have 8 over s plus 2 cubed, I'm going to have something over s plus 2 cubed, s plus 2 squared, s plus 2. Solve for a, b, c, and d. Again, a I can find using the cover-up method. Plug in s equals 0, and I get 1. Plug in s equals minus 2, cover up this term, I get b. C and d I have to work for. So again, place over common denominator. So multiply by s plus 2 cubed, s plus 2, s plus 2 squared. Denominators match up, add the numerators. The numerators have to match up. So 8 is a times s plus 2 cubed, plus bs, plus c times s plus 2, plus d times s plus 2 squared, s. All the terms have to match up, so let's start with the s cubed term. 0s cubed is equal to a times s cubed, nothing, nothing, plus ds cubed. So a plus d equals 0, d is minus a, d must be minus 1. Let's look at the s squared terms. 0s squared is 6as squared, nothing. Cs squared, 4ds squared, multiplying it all out. This has to balance. I know a, I know d, solve for c. C is minus 2. So the result is, here's the partial fraction expansion. Take the inverse Laplace transform, there's 1. This is 2 over s plus 2 cubed is t squared. I have an extra 2, so that's minus 2 times 2. 2 goes into the inverse Laplace transform times minus 2. Here's the t e to the minus 2t term. Here's the e to the minus 2t for time positive. There's the inverse Laplace transform. Now there's a couple ways to solve these problems. This is the exact solution. And in statistics, you can get repeated poles. Like if this is the time for 1 atom to decay, s plus 2 cubed is the time for 3 atoms to decay. You can do that. In circuits, the probability of having poles exactly the same is basically 0. But regardless, what you can do is, if I don't want to do repeated poles, I can change the problem. This is an engineering solution. I've got a hard problem to solve. If you have something like that, change the problem. But change it in a way that makes the problem easier to solve, but keeps the flavor of the old problem. So here, instead of having 3 poles at minus 2, I'll have 1 minus 1.99, 2, and 2.01. It's almost the same differential equation. So I'll have a real hard time telling the difference in the results. The difference, however, is I no longer have repeated poles. I no longer have to do that special case of repeated poles. Just use the cover-up method. So I now know the answer is going to look like this. Do partial fractions, I get my 3 terms. Therefore, this is y of t. And it may not look like it. This y of t and this y of t are basically the same. Take the step response, they'll look exactly the same. Almost exactly the same. So from a practical standpoint, there's basically no difference. This is another way to write the answer. This approach is preferred, a little bit simpler once you get it. This is basically the same thing. And you can compare the two if I take the 2 responses and carry it out to an obscene number of decimal places at 2.5, 5, 7.5, and 10 seconds. Here's the exact solution. Here's the approximate solution. The approximate is good to 4 decimal places, so they're not the same. But you'll have a hard time telling the difference between these 2 outputs. You've got to look at the 5th decimal point to see the difference. That is really, really clean data. If there's any noise whatsoever, I won't tell the difference. With LaPlace transforms, you can also have complex roots. Now, if you don't mind complex numbers, these are no harder than real roots. If I have complex number, do partial fraction expansion, I'll get two terms, one term and its complex conjugate. The inverse Laplace transform is twice the amplitude, e to the minus real part, cosine of the complex part, with a phase shift of the term over the minus c term. So for example, it appears my system, find the inverse Laplace transform. Well, I'll factor this. I've got roots at minus 1 plus minus j3 and 0. Do partial fraction expansion, but plug in s equals 0. Analyze, I get 1.5. Plug in s equals minus 1 minus j3. Analyze this guy using covariant method. I get a complex number. Analyze this, cover up that last term. Analyze at minus 1 plus j3. I get this complex number. And it actually works a little bit easier if you express that complex number in polar form. The inverse Laplace transform would then be 1.5, easy, twice the amplitude. The real part's minus 1, e to the minus t. Here's the complex part, cosine 3t, and the phase is the 1 over the minus j term. Phase of plus 161 degrees. So there's y of t. Now if you don't mind complex numbers, I would just use partial fractions. So that's kind of a summary on Laplace transforms. Let's look at some of the properties now. These are some of the properties of Laplace transforms, and we'll give proofs showing that these actually work. Laplace transforms are linear. What that means is if I have two functions added together, their Laplace transforms add together. Laplace transforms turn convolution into multiplication. If I convolve in the time domain, I multiply Laplace domain. And this is where Laplace transforms really shine. They turn convolution into multiplication. Multiplication is way easier than convolution. Differentiate. If I take the derivative of y, I get sy minus y of 0. If the initial conditions are 0, you just get sy. The second derivative is s squared y minus s times y of 0 minus the derivative of y at 0. Again, with 0 initial conditions, these disappear. I get second derivative is s squared y. Integration is just 1 over s. And a delay is e to the minus st times the Laplace transform of x. So here's some proofs. Suppose I want to find the Laplace transform of a f of t plus b g of t. Laplace transform is defined as the integral from minus infinity to plus infinity of your function times e to the minus st dt. Well, I can distribute the e to the minus st and treat that as two integrations. Pull out the a and the b, and I have Laplace transform of f plus Laplace transform of g times a and b respectively. Laplace transforms are linear. Convolution. Here's the biggie. If I have Laplace transform of f convolved with g, convolution is f of t minus tau, g of tau d tau. Kind of what we did in the discrete plane. If I have, here's f, here's g. What I'll do is I'll take f and flip it like this and start sweeping it. Multiply the two together, and the integral of the product is the convolution. Well, if I plug that in, I have this definition times e to the minus st. That's the Laplace transform of it. I can take e to the minus st and change the order of integration, put it on the inside. Take the g of t, pull it outside, since this is in terms of t. G of tau is not a function of t. Then I have a function of t times a function of tau. Those are two separate integrals. That'll just be f of s times g of s. Laplace transforms turn convolution into multiplication. Differentiation. If I take the derivative of x, the Laplace transform of the derivative would be the derivative of x e to the minus st. Assuming I'm causal, meaning x of t is 0 for time less than 0, just goes 0 to infinity. Now do integration by parts. I have the derivative of AB, that's a prime b plus ab prime. So the integral of a prime b is ab minus the integral of ab prime. So for this guy right here, let a prime be dx dt, meaning a is x. Let b be e to the st. Then by integration by parts, LaPlace transform of the derivative is the integral of this guy. That'll be the first part minus the second part. This is assuming x goes to 0 as t goes to infinity. This is x of 0 minus s times the integral of x of t s is e to the minus st. That's x of s. So that is the LaPlace transform of the derivative. Again, if the initial condition is 0, it's just s x of s. S times x. Integration. Same trick. LaPlace transform of the integral is, by definition, the integral of your function e to the minus st dt. Do integration by parts, where a is this part. B prime is e to the minus st. I'm going to take the derivative. A prime is just x. B is the integral of that. 1 minus 1 over s e to the minus st. So LaPlace transform be by using integration by parts. The first term, second term, assuming the function vanishes at infinity, I just get the second term, which is 1 over s, x of s. Time delay. If I have a signal delayed by t seconds, I can just do a change in variable. Let t minus delay be tau. Then this becomes tau. This becomes tau plus t. The derivative dt is d tau. Separate this, e to the minus s tau times e to the minus st. Pull the e to the minus st outside. That's the LaPlace transform of x. There's the delay. So these are some of the properties we'll be using later on. So that's kind of a summary of LaPlace transforms. You use LaPlace transforms in many different classes. What LaPlace transforms do is they turn differential equations into algebraic equations in S. They also turn convolution into multiplication. LaPlace transforms are just darn useful. They're used to analyze signals. We use them in circuits, electronics, signals and systems, embedded systems, control systems. They're used any place you analyze differential equations. In addition, they're used in random processes. If I ever need to convolve continuous PDFs, LaPlace transforms are nice. If I ever need mathematics that can describe a continuous function, LaPlace transforms are useful. Now in statistics, LaPlace transforms are called moment-generating functions, but it's really just LaPlace transform. So in this course, I'm going to be calling them LaPlace transforms, occasionally moment-generating functions. The two terms are interchangeable. The entire world calls them LaPlace transforms, except statisticians. Statisticians call them moment-generating functions, same thing. So that is lecture number 12 for ECE 341, LaPlace transforms.